Hi everyone. What I want to do this evening is share with you my experience in designing and constructing, fabricating and erecting a home observatory. I will make the point at the end that I think if anyone wants to tackle a similar project, I suspect you will be forced to follow more or less the same route. But I will take you through my reasoning. The term home observatory evokes many strong emotions, dreams, and ideas. I don't think they all start with a Keck telescope. But however wild your dreams, you are brought back to reality pretty quickly. You have to do a detailed research of the design philosophies, methodologies, and materials used by other people, including visits to other home observatories. And there are actually 3 members of the Hermanus Astronomy Center that have got home observatories that I will show photos of. If you Google design home observatories, you'll be swamped. So at the end of this very stimulating process, you eventually realize that the design of your home observatory is totally determined by the answers to a few fundamental and very deterministic questions. These are simply where or in what town and why. You've got to start with a town. Then once you've located, I did use the term home, so if you've got a home, you've got choices. Location, where on the preferred site, is also critically important. That leads to the next question: what type? A roll-off, a dome, a pillar, or whatever other alternative design you could think of. The materials that you choose need some consideration. You have to think how to construct it, how to install it, and very importantly, what are the restrictions. In my case, the where was limited to either Hermanus or Nature's Valley. And the first decision, where, was totally dictated by light pollution. Both these sites are close to the sea, with frequent cloud cover, as we know. But when the sky is clear, the observational quality of Nature's Valley is much better, primarily because of, if not zero, very, very little light pollution. This is a photograph that I took in the middle of the year in front of the house on the lawn at Nature's Valley. It wasn't perfect seeing. There was slight humidity in the air, so the focus is not pinpoint sharp, but it gives you an idea what the absence of light pollution makes possible. Jupiter and Saturn are these 2 bright ones against the drift of the Milky Way. So in my case, light pollution determined that the town or the place would be at Nature's Valley. Now, to give an idea of the next decision, where on the site you want to put it, just to put into perspective, this is a Google Maps photo of Nature's Valley. There's the Groot River Pass coming down, and here's the Groot River Lagoon, and here's the road going to the parking terrain and the beach. Now, the first 9 houses built in Nature's Valley in what is known as the syndicate are all located here. So all these houses face, there's north, so they face northeast with their front light shining there, and whenever there's passing cars, they also go past in front. You can see that most of the township is very well treed or greened, and at the back, one would typically want to go to the southwest side on the site. So the southwest dormer was a logical choice for a number of very simple reasons. It's away from the lagoon facing front houses, away from passing car lights, and from experience, there's no backyard lights visible from the neighbors. Maybe the trees help a little bit, but there were no lights visible from the preferred site. 2 very important considerations in this particular instance was the height above and the distance from closest vegetation. As I showed, there are quite a lot of trees, so you need the height to elevate your horizon as much as possible. And equally important, it's not in an otherwise used space. It would, however, require doubling of the existing dormer. This is the house, that's the dormer that I'm referring to, which would have to be doubled. This is the distance between two trusses, typically 1.1 or 1.2 meters apart, so doubling it will give enough space for the telescope to rotate in. You can also see the neighbor's trees over here, so the height is actually quite important to lift your horizon as high as possible. So where on the preferred location? There were three considerations: away from lights, the side furthest away from lights, and then height above and distance from vegetation, and also not an otherwise used space. So the southwest dormer was the logical location. What type? Roll-off, dome, pillar, or whatever. Now, the first option, which I think is normally considered, is a roll-off roof. It's a simple design in principle, but as always, as Johan can tell you, the devil is in the detailed design. It does need a roof supporting beam, which I think more or less implies that it must be constructed at ground level. It has got, which is quite an important plus, it's got a wide field of view, limited only by the walls. So maybe must be is too strong, but it frequently is the first option to consider if you've got the space, and it's relatively simple. This is a photo of the Fisherhaven medium telescope, which was sent to me and permission granted to use by the resident astronomer called Johan Retief. There's another photo of it. You can see the roll-off roof, and you can see the beams on which the roof must rest. If you look inside it, it's a timber windy house structure, the roll-off roof. Johan used a very nice, I think it's oak pier, which was machined by a neighbor down the road from him, and the telescope mounted on top of it. That's a close-up of the telescope with the mount and the camera at prime focal point. There's where the resident astronomer works. Note the mandatory cup of coffee. And it's interesting that he had to slot out space for his screen to fit into the shelving over there. But very meticulously designed, and it works well. There you can see the accessories that he uses for the observatory. Right, the second alternative which one can consider is a dome, which is superficially more complex, but when you get down to detailed design level, it probably requires about the same level of input energy. In principle, it's more compact, a circle versus a rectangle, than a roll-off dome, typically rectangular. You must be aware of the fact that the field of view is restricted by the shutter width. But the shutter, the dome, of course, blocks off more stray light. And then if you are limited to an upper story for height considerations, it's easier to install. If you go for a roll-off roof, you need support pillars. So an obvious alternative is a dome. This is a photo of the Bredasdorp photometric facility that was designed and fabricated, constructed, and installed by Andre van Staden. And he uses it quite a lot, and he's actually been given the Overberg Medal in recognition for his excellent observation work from this dome. To give an idea of the size, there is Benny photographing the dome itself. I think Derek, Benny, and I went to visit Andre and inspect his quite impressive facility. That's the inside of the dome. He uses a 10-inch Smith Cassegrain. In his case, he used a metal pipe, which is on its own foundation. You can see that it can adjust the horizontal. It uses a wedge typically on the Celestron. And the pier itself, I think, had reinforcing ribs. And then it was filled with very, very dry sand to damp any vibrations in the pier itself. The third option which one can consider is a pillar. Now, where space or aesthetic considerations are limiting, a simple cabled pillar is an alternative. Now, if I think back 30 years ago, Cliff Turk gave one of his first talks. He was a good friend of Steve Klein, and he gave a talk here and he showed his simple facility in the backyard of his garden in Pinelands. And once again, I think Derek and Benny, Peter and I actually visited a similar site in Betty's Bay. Obviously, it's very compact, and normally it can be controlled, where you design it so it can be controlled from the comfort of your house. It is definitely the cheapest and the simplest of all designs. To show an example, this is Pete Scully's pillar observatory in a retirement village in Howick. Now, because he's in a retirement village, he didn't have the space to consider a roll-off roof, which was his first observatory while he was still in the Transvaal. He had a similar one at Betty's Bay, and now at Howick he's repeated the concept. This is actually a PVC pipe, which is filled with reinforced concrete and rods. And obviously it's instrumented, the cables go through the center of the pier, under the ground and into his house. There's its raincoat on. They've had quite a lot of rain in KZN recently. And there is his mount. Adjusting mount, taking quite a lot of trouble to align it once, and then he can use it repeatedly. The telescope obviously fits in there. In my case, the key considerations for what type were, I was basically restricted to the upper story or second floor. And then very importantly, it had to form part of a permanent structure, namely the house. So that had quite an important impact on the materials considered, because it's got to last for quite a long time. And then it is quite compact, particularly if you're going on to the second story. So in my case, the choice was to go for a dome. But you can also see, if I take you through the arguments, it is more or less an inescapable conclusion. So what construction and material options are there? Just comparing notes with other people, Johan Retief did his own design, and he used subcontractors under his direct and everyday supervision to construct and erect his observatory. Andre van Staden did the design and construction and installation himself, as did Pete Scully in Howick. In my instance, the long distance, almost 500 kilometers away, long distance supervision and becoming part of a permanent structure dictated the most practical approach for this site. For this site is quite an important term. I decided to use my own labor for the detailed design. It's cheap, and I can't blame anyone else for mistakes if they are, they're my own making. Not surprisingly, I opted for precise laser cutting of durable stainless steel. We've had quite a lot of experience with that process at the various sundials at the Hermanus Astronomy Center, as designed and constructed and erected, in fact, throughout the country. And I wanted to minimize subcontractor unilateral decisions. I think everyone that's been involved with a building project knows that unilateral decisions are taken on a daily basis. One wants to limit that as much as possible. And then, quite important, to use an experienced marine subcontractor for the glass fibering. Once again, because of the permanent nature of the structure, I can't do it, so I decided to use the best available marine subcontractor. They do boats, that's the main line of business. The detailed design is quite a loaded term. If we look at the options that you had, the dome support structure had to fit onto the 2-bay dormer, which implies a width of 2.33. And there's nothing you can do to change that. Once you've chosen the site, the position of the trusses on either side of the dormer determine the width of your dome. I did have the freedom to choose a shutter width, internal shutter width, and I chose 700. That's one of the 2 degrees of freedom that I had. And also, the second choice that I had was to choose the best appropriate SKF bearings on which the whole structure will rotate. Some of you might remember that in my mobile observatory, I called it the 1DF because there's only 1 degree of freedom, and that's the length of the trailer. In this case, it could probably be referred to as a 2DF dome because there are only 2 degrees of freedom, the width of the shutter and appropriate choice of bearings. For the rest, the geometry is fixed and you must just draw it out. In plan, you can see that the shutter window of 700 millimeters internal, the shutter guides, which are supported with shutter guide supports at 45 and 90 degrees all the way around. And there's not much that you can change to that. I suppose you could use more support structures, but with 3 millimeter stainless steel, it is quite strong and rigid. All of this rests onto a hot-tipped galvanized fixing frame, 38 by 76. You can see the black outline, and you can see that the fixed base of the dome is actually epoxied and pop riveted because it's 38 by 76. You can't bolt it. In any case, the holes were pre-drilled because of the precision that laser laser cutting gives you. The most complex elements of the structure are the 2 shutter guides, which actually have 3 different outer radii, and they have different 2, 3, and 5 by 20 millimeter nibs to fit into positioning slots. Those of you that have experience of working, constructing with stainless steel will know that the TIG welding that is required for stainless steel generates very high temperatures. And stainless steel deforms very easily at high temperatures. We learned it to our dismay at the sundials at Sansa. In any case, so the fabricator told me I must actually design in and have slots 4 by 20 millimeter and nibs to fit into those slots, just to position. So it's more or less, once it's been laser cut, it's fitting together a 3D Meccano set. To give an idea of what it looks like, internal radius 1038. There's the guide cover. First of all, that 77.5 degrees is permanently covered, and then the shutter guide moves over, so you can look from 25 degrees to 105 degrees. And of course, because you can rotate the dome, you can see everything 25 degrees above this line. And different nibs. This one had 4 nibs, that part had 4 as well, and this part had 3. So it's quite complicated. You can also see that there are 5 millimeter holes drilled to take stainless steel brackets, which were equally designed and laser cut and we just fit together. So you've got to put quite a bit of thought into the detailed design and how everything fits together. If we look at the detail, there's the fixing frame. And then one of the degrees of freedom is the choice of bearings. This is a 25.4, in other words, 1 inch stainless steel roller bearing, which is embedded in actually a bed of smaller roller bearings. So it's as close to frictionless as I've ever experienced. This is also, I think that's about a 7.9 or 8.9 millimeter roller bearing, equally embedded, but that determines that distance. So you couldn't do the detailed design before you knew exactly what particularly that bearing was going to be. So there's the fixed base in the form of an annular ring and a rotating one which rotates on it, on the bearing. That's the plan. Now let's look what it looks like in reality. You can see this is the fixed base with the vertical roller bearings, and you can also see the horizontal one to control the lateral movement. So that's the fixed base. This is the rotating base, which fits onto it, obviously. There are the shutter guides with their support arcs, and lots of holes drilled everywhere so that you could just bracket them together. Looking at some of the detail, this is a 45 shutter guide support, which is bolted onto the shutter guide itself. Couldn't actually put in bolts and nuts there, so that was just, it was firm enough in any case. Here you can see one radius stepping out by 2 millimeters, and another, there's a nib, and there's the slot. The 90-degree support, you can see there are the holes for the brackets to be bolted onto. That's a tack weld, just when it was put into position. This is the same view from the other side. There you can see the nib is inside the slot, and there's the tack weld. And in fact, these brackets were a bit of an overkill, so they weren't used in all instances. Now, this one, just to give an idea, when you put the rotating dome onto the fixed dome, you can see from the effort of the fabricator that it actually rotates quite easily. It's lighter than the final one, obviously, so it rotates easier. All right, now to get to the glass fibering. It's quite an interesting process, but this is the way they make all marine glass fiber boat hulls and things like that. You start off with well, chicken and egg, but you've got to have a balloon to support the structure onto which you apply the glass fibering. And yeah, this is being stitched together, put together. There is the balloon that you can see. Then the pattern, as he calls it, is 3D laser printed, flexible material onto which the glass fiber will be applied. And you put all these segments together and you get a sphere of 2.33 millimeters in diameter, 2.33 meters in diameter. And there it's been glass fibered all over in the workshop of Loma Marine in Plettenberg Bay. And he actually used the lockdown. He was due to start the day before lockdown happened. He was so frustrated at home that he went in on his own, and he actually did this installation during lockdown. So when everything opened up, the project could continue. And there is now the complete, that's back at the fabricator's workshop. And there you can see the complete, almost complete without the shutter rotating. It's almost complete, but you can see that the effort required is not too much. To give an idea of how the shutter moves, here's the fabricator inside. And note this rubber. He had a much more practical solution to what I had in mind. But in any case, this works very, very well. Right, the dome has been fabricated, and there it arrives at its final location, if on the final site, if not at the final location. It was quite a cold morning in end of June, and 3 of these helpers actually traveled inside the dome from Plek to Nature's Valley because it was cold. Then to install it, it was manually done because I think the total weight was less than 150 kilograms. So it was quite easy to handle by, in this instance, 5 guys. The first step up into scaffolding, the second step, and the final step. Just getting it, putting it over the fixed base, and then it is finally installed. Seen from the back, you can see that this dome has been doubled in width. This is seen from the neighbor side. Same dome as all around, but you can see the trees. Why that location is approximately the furthest distance and at the highest height that you can get from the vegetation to maximize your horizon. This is a view from inside. In this instance, it was a blackwood pier, about 180 millimeter in diameter. That is turned from this base, which is totally loose from the floor. And there's the dome inside. This is what supports the base. That's 180 by 180. It's just a cover, but these are 76 by 228 beams bolted onto the pier, and these are slotted into the walls and wedged. No bracket bolts or anything like that, wedged in, which is used quite extensively by this guy. He's absolutely a master craftsman, called a finishing carpenter. Now you've got to instrument it, and to that end, this 20 by 20 millimeter rectangle was slotted in inside of it. Unfortunately, when it was installed, and I only discovered that when I got there to install the cables, it was blocked. So it was quite an effort to get it open again. But you can see all the cables coming through there. These are just loose aluminium 90-degree angles, just to round off because there's a gap between the pier and the floor itself. And then all the cables fit inside this 50 millimeter conduit and fits in there, and then this fits on the floor as well. Behind here is the deep cycle battery, inverter, and lots of multi-plugs, and so that you can connect to the controlling laptop. This is the next step. Maybe I'll just go back to point out the difference. This is, you can see the timber pier. Those are the 3 mounting screws. That is true north. Okay. And this is with the mounting bracket simply screwed onto it. And the telescope, it's M8 bolts that go in there on which the telescope mount fits. I did make the point that it was not an otherwise unutilized space. This is the northeast dormer, which is more or less a mandatory early morning coffee or tea position to watch the sunrise in winter or just to enjoy the view in summer. Note the baboon burglar bars, polyurethane, because there are lots of baboons. Actually, it's a bigger problem at Nature's Valley than in Amanas. And this is the southwest dormer, which you can see would not be used. It's not very amenable to alternative uses. So, and it's got a back view, which is just to the back buildings. This is where the resident astronomer sits and works, the laptop on this beautiful old Oregon pine. As much wood was recycled as is possible. You can see holes drilled through for laptop cables and for electrical cables to the plug over there. And there's the pier. And there it is installed. It's a bit of a messy photograph, but it does give you an idea. It's been slightly amended now, and it's been lifted higher. That all has been constructed, but the last time I was there, we had visitors all the time, so I couldn't do what I wanted to do, actually. The fundamental lesson learned from the whole process, and I think if you follow the logic of my decision-making, is that each home observatory is absolutely unique to cater for its specific conditions and constraints. If you just think of Johannes Roelof's dome, you think of Andre van Staden's dome, you think of Pete Scully's pillar, and in this instance, I was more or less led to install a dome. My experience is also that when you consider all the options, you do the detailed design, and I suspect that you end up with the same optimal design 99 times out of 100. I haven't tried something else, so that's not a substantiated statement, but I think it's a fairly reasonable conclusion. So what next? First of all, we must automate the dome and the shutter control. This has all been made, fabricated, but I just didn't have enough personal time to actually install it. This is a Toyota wiper motor with an 8mm shaft, and you're bearing quite nice rubber which will roll against the rotating dome to rotate it. The next step, which is ongoing already, is maybe train and convert. The conversion part is more important, the next generations, and there are two of them, to enjoy and love amateur astronomy, not just observational astronomy. And then finally, most importantly, the intention is to have loads of fun and lots of photos. That's my story. I do suspect, as I said at the beginning, that if any one of you are considering doing a similar project, it's fun, it's very rewarding, and I think you will be forced to more or less go through the same process as I was forced to. Thank you very much.
Thanks, Pierre. Anybody got any questions?
Yeah, I was just wondering, Pierre, the waterproofing of that dome, I presume that that's pretty well 100%, right?
Yes, I think the main thing, where do I get this down? Can I stop my screen sharing?
Yeah, stop your screen sharing and just share something else that you want to show.
I actually want to stop share. All right, so there we're back to. Peter, your question, first of all, if you think back, I could look for the photograph very quickly. The dome itself, what am I looking for? this one, the outside dome extends beyond the fixed dome. So all the water coming from top is going to flow past the inner dome, and you've got a height of about 100 millimeter to prevent water spillage. So nothing will come from the dome. You have to waterproof the shutter. And if you look at the detail, you can see there are edges along the shutter which overlap here. So once it's closed, it's pretty well waterproof. And there have been quite severe rainstorms since we've been there, and I've obviously observed it to make sure that there are no leaks, and there definitely aren't any leaks. But this concept is quite important. I got that from Andre van Staden's design, and it works very well.
Yeah. I don't want to hog the question time, but there's one more question you probably laugh at, but maybe not, I don't know. Any chance of getting a remote control from Hermanus to operate this thing? Obviously, it would be quite an operation.
Yes, the answer to that is, I didn't think of it initially, but the project manager or the builder in Nature's Valley actually suggested it to me. Now that is why, amongst the things to do is to automate the rotation of the dome and the opening and closing of the shutter. And that I must still do, spend some time alone and do that. But it's not that simple. When you're controlling something from Hermanus, almost 500 kilometers away, you must make sure that you're catering for all possible errors, because Murphy will ensure that whatever can happen will, and that you can provide for that. So the intention is to eventually try and do that, but that's quite far into the distance, in the distant future.
You need to have a weather station. You need to know if it's going to rain or if the wind's blowing and all kinds of things, and act according to that as well.
Yes, I think our experience with the mono telescope showed that an all-sky webcam is actually quite important. But then also you must cater for the many load-shedding instances. Now the inverter should cover that, but it takes a lot of thought, and it'll have to be tried on site while there's someone there to fix up things before I'd actually do it from Hermanus. But the intention is to eventually try and get there.
Problem is Murphy may be a baboon.
Very true, very true.
And he may be assisting. Pierre, may we ask you an approximation of cost?
More than a good bottle of whiskey.
Okay, that's expensive. Okay, thanks a lot.
If anybody has joined late, I have recorded the whole thing and will make the video available.
Thank you, Derek. That applies to me. I had one of those days.
Pierre, baie dankie. It was baie interessant. Thank you very much indeed.
Okay.
Thank you, Pierre. That was excellent.
All right. Now I'll leave you to think about your own home observatory and ask the same questions of yourself.
Thank you,
very
Pierre.
much, Pierre. That was fascinating.
Thank you very much, all.
An
Thank
awful
you.
lot of work.
Okay, bye.
Bye, everyone.
Bye-bye.
Bye-bye.
Yeah, thanks.
Thanks, Pierre. Now we know who to get as a consultant for our design.
Thank you, Derek.
Bye.
Thank you very much from Kevin.
Okay, thanks, Pierre. Thanks, everybody. If there are no more questions, I'm going to end the session now.
Lovely. Thanks, Diane.
Bye. Thank you, Derek.